Today, we're exploring an absolute game changer in modern science, UV-vis spectroscopy in nanotechnology. When we're dealing with the nanoworld, working with stuff incredibly smaller than a human hair, our eyes just don't cut it. We need a fast, non-destructive way to measure exactly how these nanomaterials absorb and scatter light. Honestly, this technique, it's basically a superpower for characterizing the invisible. So here's our roadmap for today. We'll start with the spectrophotometer setup, move right into the working principle, and then check out surface plasmon resonance. After that, we'll dive into 5 key nanotech applications, and finally wrap up with why this is such a simple yet powerful tool. Now, consider this our master blueprint. I know, at first glance, a complex lab setup with all its charts, optical paths, and formulas can look a bit intimidating. But don't worry, we're going to break this whole thing down logically. By the end of this, you'll have a crystal clear understanding of what this machine is, how it ticks, and exactly why it's absolutely critical in nanotech. All right, Section 1, the spectrophotometer setup, tracing the light's path. The whole journey kicks off at our light source, which pumps out both UV and visible light. This raw white light squeezes through an entrance slit and hits the monochromator. You can kind of think of this like a high-tech prism. It disperses the light into this beautiful spectrum of individual wavelengths. Then an exit slit picks out just one specific wavelength to shoot straight through our sample cuvette, where our nanomaterials are just hanging out in a liquid dispersion. Whatever light actually makes it through the other side without getting absorbed or scattered, well, that's captured by the detector, which immediately translates that physical light signal into digital data on your computer screen. Moving on to Section 2, the working principle. Nanoparticle interaction. To really make sense of this, imagine this sample cuvette as a microscopic obstacle course. We start off with the incident light. We call that I0. This is the strong, completely unobstructed light entering the cuvette. But inside, our nanoparticles act as the obstacles. They're absorbing and scattering that light left and right. So the light that actually survives the course and comes out the other end, the transmitted light, or just I, is noticeably weaker. The detector's whole job is basically to measure the difference between what went in and what came out, and it records that difference as absorbance. And that brings us to the fundamental math running the show here, the Beer-Lambert law. Now, I know equations can look dry, but this one's actually super elegant. A stands for absorbance, which is just the logarithm of our incident light divided by our transmitted light. Simple enough, right? But look at the second half. Absorbance also equals epsilon times L times C. Epsilon is the molar absorptivity, basically how inherently good your specific material is at soaking up light. L is the path length, just the physical width of the cuvette itself. And C is the concentration of our nanoparticles. So this one single law is literally the key. It lets us calculate exactly how much material we have in there, simply by measuring the light that manages to escape it. Section 3, surface plasmon resonance, the optical fingerprint. Okay, check out what I like to call the golden motif. What you're seeing here is a classic UV-vis absorption spectrum for gold nanoparticles. Notice that massive, super distinct mountain peak right around 520 nanometers? That right there is the surface plasmon resonance, or SPR peak. Basically, when light hits these noble metal nanoparticles, it forces their surface electrons to collectively oscillate. They're literally dancing in perfect harmony with the light wave at a very specific frequency. For gold, that magic number hits right around 520 nanometers. It is a completely unique optical fingerprint. Section 4, 5 key nanotech applications, real-world nanotech. Now, what's really interesting here is just how much this tool can actually do. We're going to look at 5 distinct superpowers this single technique gives researchers. Ready? 1. We can confirm nanoparticle formation. 2. Determine their size and shape. 3. Calculate band gaps. 4. Track aggregation and stability. And 5. Monitor synthesis in real time. Let's break these down one by one. Application number 1, confirming formation. Because of that highly unique surface plasmon resonance we just talked about, we can instantly tell if our nanoparticle synthesis was a success. If we're trying to make gold nanoparticles, we just pop the sample into the machine. Boom, a strong peak at roughly 520 nanometers. We nailed it. If we're cooking up silver nanoparticles instead, we'd be looking for a peak at about 400 nanometers. It's a rapid, definitive, yes or no test right there on the screen. On to application 2, determining size and shape.
So if we have small, perfectly spherical nanoparticles, we get this nice, sharp peak pushed toward the left side of the spectrum. But if our particles start growing larger, or maybe they stretch out into these rod shapes, that peak does two very specific things. First, it widens or broadens out. Second, it shifts toward the right, pushing into the higher red wavelengths, which is exactly why we call it a redshift. By just glancing at how wide the peak is and where it sits, researchers can literally see the shape and size of particles that are way too small for a standard microscope. Pretty cool, right? Application 3 is band gap calculation. Now this one is absolutely crucial for semiconductor nanomaterials and quantum dots, the stuff powering everything from advanced solar cells to your modern TV screens. By plotting our absorption data onto a specific type of graph called a talc plot, we can zoom in on the sharp absorption edge. If we draw a straight line, just extrapolating that edge down to the horizontal axis, we can accurately determine the optical band gap. Honestly, it's just an incredibly elegant way to figure out a material's electrical properties using nothing but light.
Application 4, aggregation and stability tracking. Let's be real, nanoparticles can be pretty finicky. Sometimes they clump together like awkward guests at a party, and that completely ruins their special properties. Well, UV-Vis acts as an early warning system here. A perfectly stable dispersion is going to give you a beautiful, sharp peak, but if those particles start to clump up and become unstable, that peak gets damped, meaning it drops in intensity, and noticeably broadened. So the crucial point is that one quick scan instantly tells us the exact health of our sample. And application 5, real-time synthesis monitoring. This brilliantly illustrates the dynamic power of the spectrophotometer because we can actually watch reactions happen over time. At minute 0, you've got very little absorbance. But as the minutes tick by, moving from that initial nucleation phase through particle growth and finally hitting completion at 100 minutes, you'll see the absorbance peak climb higher and higher. You are literally tracking the growth kinetics of your nanomaterials in real time, right as the solution turns from clear to a deep red in front of your eyes. Section 5, a simple, powerful tool, summarizing UV-Vis. So this perfectly summarizes the analytical journey we just took. Think about it. We start with a relatively simple process, shining a light through a sample. That gives us a single absorption spectrum curve. But from that one simple curve, we are unlocking massive amounts of complex data. We're confirming formation via SPR, determining size and shape, calculating band gaps, assessing stability, and monitoring synthesis kinetics. It is quite literally a masterpiece of analytical efficiency. We've seen how tracking something as incredibly basic as absorbed light can reveal the hidden geometries, the stability, and the fundamental physics of materials that are thousands of times smaller than a cell. The tools to see the unseen are right in front of us, elegantly governed by the laws of physics. So I'll leave you with this. How will you use this simple, powerful tool to unlock the invisible complexities of the nanoworld? Thanks so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.